So the last chapter for this unit is chapter 9. We're going to be looking at bonding. So we really haven't talked about how, especially in covalent bonding, how the electrons are shared. So we'll focus in on that right now. So there's two approaches to bonding, chemical bonding. One is called the valence bond theory, and the other is the molecular orbital theory. So the way they're different is the location of the electrons and bonding orbitals, the energy of the electrons, the presence of unpaired electrons in the molecules. So molecular orbital theory is actually more accurate, but it's pretty complicated, so we're not going to cover that one. And then the valence bond theory is easier to use, so we're just going to focus on that one. So valence bond theory. Valence atomic orbitals. So it's all about the valence electrons, not the core electrons. And they end up overlapping. Their orbitals will overlap. And then when they do that, they are filling a half-filled orbital to be a fully filled orbital. So I'll kind of draw a picture of that for you. The VSEPR theory doesn't really explain why the bonds exist. It just kind of shows us the geometry. So the valence bond theory gives us a better idea. So we need two electrons to be able to form a chemical bond. So here's an example. We have two hydrogen atoms, and we know for hydrogen they both have a half-filled orbital. So just to draw that here. So here's one hydrogen, here's the other, okay? So they both have one valence electron in the 1s orbital. So they're both half-filled, and you have to have a half-filled orbital in order to make a bond. So they have the s orbitals, right? So here's the s, and they both have one electron. So to form, this bond right here between the two hydrogens, what these s orbitals do is they overlap, and the electrons, that didn't look very good. I'm going to change colors here. The electrons are shared between that overlap. So one electron is attracted to the nucleus. So I'll put the nucleus here and here. So one electron is attracted to the opposite nucleus, the other electron is attracted to the opposite nucleus, and that's what holds that bond there. That's what holds those atoms together in that single bond. So remember, only half-filled orbitals can make a bond. Okay, I'm getting a couple more examples. Okay, here's another example. So here we have hydrogen with its 1s orbital and fluorine. So fluorine's valence electrons are found in the p orbital. So let me draw this one for you. Okay, so here we have hydrogen. Let's go back to black here. Not that one, that one. Okay, hydrogen with its 1s. Okay, and then we have fluorine. And fluorine's valence electrons are in the 2p. So just to give you the electron configuration, 1s2, 2s2, and 2p5. Okay, so the valence are in the 2, but specifically the half-filled orbital is in the 2p. So we have 3 orbitals for 2p, and we have one half-filled orbital. So the overlap is going to occur with this p orbital right here. Okay, so we have hydrogen's 1s with its electron. So we're going to put that there, and then I'm going to come in with the p orbital. Not real great at drawing there. And we'll change colors, and this will be the p orbital electron there. So they form that bond, the HF, right here in that overlap. So it happens with the half-filled orbitals. Okay, now we're going to get into hybrid orbitals. I'm going to give you a little more explanation than what you need, so I'll kind of sum it up after I talk about hybrid orbitals, exactly what you need to know for the test. So sometimes the atom does not have all the half-filled orbitals that it needs to form as many bonds as it needs. So we're going to start with the hybrid orbital with carbon first. Okay, so here CH4 in this molecule, carbon needs 4 half-filled orbitals to be able to form 4 single bonds. So let me draw this here. Okay, so we have CH4, and I'm going to give you the electron configuration of carbon. So carbon is 1s2, 2s2, 2p2. Okay, so really I'm looking at this one right here, right? The half-filled orbitals. Okay, so 2p, we only have 2 electrons. So there's really only 2 spots where I can form a single bond, where I can form that overlap. I can't do anything with an empty orbital. So how do I make all 4 of these bonds with just 2 half-filled orbitals? Okay, so what happens is carbon will form a hybrid orbital. So it's going to form an sp3 hybrid orbital. So what it does is it takes the s subshell and the p subshell and it puts them together to form this hybrid orbital. So just to show you this, so carbon has, so we're only looking at valence. I'm going to leave out 1s. We have 2s, we have 2 electrons in the 2s, and we have 2 electrons in the 2p. So they come together, it's because it says sp3, right? sp3. So that 3 is not how many electrons are in that orbital, that's how many p orbitals we're using. So we're using 1s in all 3 of our p orbitals. So we're going to combine all 3 of these to give us 1, 2, 3, 4 orbitals. So I get that from, here's 1, 2, 3, 4. So I'm just putting them all together in this sp3 hybrid orbital. Okay, so then to know how many electrons I have, I just count up the electrons in the sp orbitals. I have a total of 4. So now I'm going to place those using Hund's rule in the sp3 hybrid orbital. So I'm going to place 1, 2, 3, 4. So I have 4 electrons, 4 half-filled orbitals that can now form an overlap. I'm not going to try and draw the tetrahedral shape because it's not real great when I draw it, but you can see there with the tetrahedral shape that sp3 hybrid orbital makes. So now I can have 4 hydrogen come in and overlap like this. So they're overlapping with their s orbitals, and now that bond is formed because those electrons are being shared in that overlap, and we get the tetrahedral shape. So that's the sp3 hybrid orbital. We take all the s, all of the p orbitals, and we put them together in the sp3. Okay, sp2, and just like I said, the 2 represents how many p orbitals we're going to be using. So we'll use 1s and 2 of the p orbitals. So we're going to do that for BF3. So let me come back here. I'm going to give you boron's electron configuration. It is 1s2, 2s2, 2p1. Okay, so there's only one half-filled orbital in the p subshell. So we've got, and again, I'm just going to use the valence because that's all that's involved in bonding. 2s, 1, 2, 3, and 2p. So 2s is filled, and I only have 1 and 2p. So really, there's only one spot that I can form a bond, but I need 3 bonds. So we're going to take 1 of the only s, and 2 of the p, and we're going to put them together in the sp2 hybrid orbital. So sp2, because I only took 2 this time instead of all 3. So then again, I'm going to add up all the electrons that are in those orbitals that I just put together, which I have 3. And now I have 3 places I can make bonds. 3 half-filled orbitals. So here's that. It has a trigonal planar shape. Okay, so it has those 3 lobes. And then I have BF3, so fluorine now can come in and overlap. Remember we looked at fluorine, and its half-filled orbital was the p orbital. So that p orbital comes in and overlaps with our hybrid orbital, the sp2 hybrid orbital. Okay, the last one we're going to draw is sp hybrid orbital. So we have beryllium. Okay, beryllium's electron configuration is 1s2 and 2s2. So beryllium, just looking at the valence, okay, we have 2 and 2s and nothing in 2p. Okay, but we are going to take the 2s and the 1 of the p, and we're going to make sp hybrid orbital. So I just have 1 s and 1 p. And again, we're going to take the electrons that are in those orbitals that we put together. And now I have 2 half-filled orbitals for beryllium to make single bonds with. Oops. Okay, so now fluorine can come in and BF2 and overlap with its p orbital to form those single bonds. There it is. Okay. So the sp has a linear shape. Oh, I forgot to mention one thing. So let me go back to this. I'm probably not going to ask you anything on this on your test, but your homework asks about it, so I want to just mention it real quick. Here, I have 2 p orbitals that we didn't do anything with, that are not a part of the hybrid, right? So we call these unhybridized. Whoops. Okay, they are unhybridized. We did not use them in the hybrid orbital. So for the sp, we have 2 unhybridized p orbitals, and then the sp2, we had 1 unhybridized orbital. But in sp3, all of the p orbitals are being used, so there aren't any unhybridized orbitals in sp3. So again, that's going to be something for your homework. And just so you know, the unhybridized p orbitals are usually used as a double bond, or what we call a pi bond. So we'll come back to that, because we haven't talked about pi bonds yet. Okay, so here's what I want you to know. I'm not going to ask you to show me the hybrid orbitals or anything. I just want you to tell me which hybrid orbital is needed for what, a molecule given. So all you have to do is draw the Lewis dot structure and then figure out how many domains you have around that central atom. And then you can figure out what your hybrid orbital is needed, or what hybrid orbital you need. So here, if I have 2 domains, then I need an sp hybrid orbital. If I have 3 domains, I need an sp2, 4 domains, sp3, 5 domains we didn't talk about, but you would now go into the d orbitals, so you would need sp3d. And then 6, you need sp3d2. So basically, I'm just going to give you a question with a molecule and ask you what hybrid orbital is needed for the central atom, kind of like in our examples right here. Okay, so I'm going to do these real fast. Okay, so XeF4. Oh. Oh, I went too high. Okay, XEF4, when I get done drawing the Lewis dot structure, I'm going to find that I have 6 domains. Okay, I'm not going to put the dots on the fluorines, but around the central atom I have 6 domains. So that means I need an sp3 d2 hybrid orbital. So as long as I get the domains right around my central atom, then I can easily figure out what hybrid orbital I need. Okay, and then CH2O looks like this. So I have 3 domains. So I'm going to need an sp2 hybrid orbital. Okay. And then BRF5. Okay. BRF5 has a lone pair on bromine. So we have 6 domains, which we saw earlier means we have sp3d2. Okay, and then SF6. We have 6 fluorines. We do not have any lone pairs, but that gives us 6 domains, so we're going to need the same thing, sp3d2. Okay, and then BR3. Okay, here we're going to have 3 lone pairs on the central bromine, so that gives us 5 domains. So 5 domains, which means sp3d.